In this video, we'll learn about the different conformations or arrangements of alkanes and how we can depict those conformations in flat two-dimensional structures using Newman projections. This stuff is kind of cool, but it can be hard to see in 2 dimensions at first. So I definitely recommend that you have your model kit with you as you watch the video, and that you pause the video occasionally to build some of the structures that we'll be looking at. Conformations are different arrangements of a molecule in space that result from rotation around bonds. And when we talk about rotation around bonds, we have to be clear that we're talking about sigma bonds or single bonds, because we cannot rotate around double bonds. When there's rotation around a single bond, it results in new arrangements of atoms in space, and we call those arrangements conformations. We call the molecules that have different arrangements of atoms conformers. Conformers refer to the molecules. Conformations refer to the actual arrangement of atoms. And I was using a model as I talk because it's one of the easier ways to visualize the arrangements of atoms in 3 dimensions. But to depict a conformation in 2 dimensions, we use what we call a Newman projection. I'll use ethane as an example to show you what a Newman projection is. When we draw a Newman projection, we imagine that we're looking down a carbon-carbon single bond of ethane. Okay. And I'll use this color-coded ethane that will match with the structure that we're looking at on the screen. To depict looking down a carbon-carbon bond, we draw a little eye on one side of the molecule. And that's what this blue thing is. This is an eye looking down the bond from the left carbon to the right carbon. And remember that we have 2 hydrogens that are in the plane of the paper or the screen. And we have 2 hydrogens pointing out toward you and 2 hydrogens pointing back away from you. So now for viewing the molecule from left, we're going to view down the carbon-carbon axis. And the back carbon is the carbon bearing the blue hydrogens, and the front carbon has the red hydrogens. And so we start by drawing the back carbon here as a blue circle, and then the front carbon closest to the eyeball as a dot. And now let's just look at the back carbon. We've indicated in blue, and you see as you view down this front carbon to the back carbon, looking at the back carbon, we have 1 hydrogen pointing straight up and 2 pointing down. 1 pointing down to the left and 1 pointing down to the right. Then on the front carbon, we have 1 pointing down and 2 pointing up, 1 to the left and 1 to the right. And we have a distance between these 2 hydrogens, the red one and the blue one, where they're as separated as they possibly can be. And that distance we call a dihedral angle. And that dihedral angle here is 60 degrees. And when that dihedral angle is 60 degrees, we call that a staggered conformation. So that's our first Newman projection of ethane. We said that conformations come from rotating around single bonds. So from here, from this staggered conformation, if we rotate around the carbon-carbon single bond, we get a conformation in which the hydrogens on the 2 carbons have no space between one another. They have a dihedral angle of 0 degrees, and we call this an eclipsed conformation. This front hydrogen is eclipsing the back hydrogen. Okay, as it's drawn on the screen, the hydrogens are pointing down in this fashion. And just for clarity, we can draw the eclipsed conformation with our dashes and wedges. And what you see is that we have the same structure, but a different arrangement of the groups in space. So in this conformation, our eclipsed conformation, we move it to the side, and then we have 2 carbons and 2 hydrogens that are in the plane of the screen, and then we have 2 hydrogens pointing forward toward you, and 2 hydrogens pointing back away from you. Okay, so now we're equipped to answer this question, to draw a Newman projection of this molecule looking down this carbon-carbon bond from left to right, as is shown with the blue arrow. And when you draw this, we need to be sure to maintain the same conformation as is shown in the structure. We'll start with the back carbon and indicate it with a circle. And then we'll denote the front carbon as a dot. And here I have a model with different colored groups on it. Each carbon has one hydrogen. And I'll look down the structure this way. And what I see is that on the back carbon, I have a hydrogen pointing up, I have a bromine pointing down and to the left, and a fluorine pointing down and to the right. On the front carbon, I have a hydrogen that's pointing down, I have a methyl group pointing up and to the left, and a chlorine pointing up and to the right.